Welcome. Yeah, here we have another question before us, and this is also a question on electromagnetism. All right, so it's one of the many questions in the A level, A level physics. Um, okay, now we have a student is doing an experiment on the magnetic force experienced by a current carrying wire in a uniform magnetic field. Okay, the magnetic flux density B can be varied. Now, for a particular flux density, the current in the wire is 2.0 amperes, which is the unit of electric current. All right, so now we have the length of the wire in the field is 0.12 meters. Now, the angle between the current and the magnetic field is 30 degrees. So between the current and the magnetic field, if you have, let's say this is the magnetic field, okay, we have the magnetic field, and then we have the electronic current. This is the current. So the angle between the current and the magnetic field is 30 degrees, okay? That's 30 degrees. 30 degrees. All right. Now, the force experienced by the wire is 7.7 multiplied by 10 to the negative 2 Newton. Now, the student calculates B and record the result in a table. Now, which row shows the correct table heading for B and the correct value for B? Now, we have the table heading for B and the value for B. So which one of these selected response is the answer, is the value for B? Now, to be able to calculate the value for B, now, we need to first identify some of the parameters we are given. Now, we are giving the current. We are giving the current, okay, current, which is I, that is equals to 2 amperes. Now, we're also giving the length of the wire. The length of the wire. So the length of the wire is given to be that will be 0.12 meters. That's the length of the wire. Then also we are giving the angle between the current and the magnetic field, which is 30 degrees. That's the angle of inclination. So the angle of inclination, let's designate that with the Greek letter theta. So that will be equals to 30 degrees. All right. So now the force experienced by the wire is 7.7 multiplied by 10 to the negative 2 Newton. So we're also giving the force on electric current, or the force on the wire carrying current. All right. So the force on the wire carrying current, that's F, is equal to 7.7 multiplied by 10 to the negative 2 Newton. The Newton is the unit of force. So the student calculates B and record the result in a table. All right, so we have the table. This is the table. Okay, this is the table. This is the table. Okay, now, so this is the table. This is the table. Okay, so one of these selected response will be our answer. One of these response will be our answer. So we have our selected response. So now, so we want to find the magnitude of this guy, B. We want to find the magnitude of this guy. And remember, the unit of B is Weber per square meters. And 1 Weber per square meter, 1 Weber per square meter is equals to 1 Tesla. So which means the unit of B is Tesla. So which means whatever we calculate as the value of B, okay, as the value of B, the unit must be Tesla. It must be Tesla. So we have B. Now we have B slash Tesla. It means the unit selected for B for each response is, now for the first option we have Tesla. Second option we have Tesla. This one is Weber. Option C. Now option D we have Weber. So in this case, to be able to calculate B, now what is the force on a wire carrying current? That's the formula for calculating force on a wire carrying current in a magnetic field. Now, the formula for calculating force on a wire carrying current is F equals to BIL sine theta. BIL sine theta. Remember, when the inclination is between 0 and 90 degrees, okay, that is when this formula, okay, will be what? Can be used. But when the inclination is exactly 90 degrees, then it will be F equals to BIL. That's when the force becomes maximum. Okay, that's when the force becomes maximum. So we know that I is 2 amperes. We know that L is when the force becomes maximum. So we know that I is 2 amperes. We know that L is 0.12 meters. Then we know that B is what is the unknown, that's the missing value. Then we also have F to be 7.7 times 10 to the negative 2 Newton. So we have 7.7 times 10 raised to the power of negative 2 equals to B multiplied by I, which is 2 amperes, multiplied by L, which is 0.12, then multiply by sine 30 degrees. Now, this is important. Sine 30 degrees is equals to 0.5. Sine 30 degrees is equals to 0.5. Okay, is equals to 0.5. So this would be 7.7 times 10 to the negative 2 equals to, so this would be B, okay, multiplied by, now 2 multiplied by 0.12, then multiply by 0.5. So 0.5 times 2 will be 1. So this is 7.7 times 10 raised to the power of negative 2. So this is 1. So we have B multiplied by 0.12. Now, then we have to divide each side. Okay, divide each side by 0.12 because we want to obtain the value of B. So we divide each side by 0.12. So 7.7 times 10 to the negative 2 divided by 0.12 equals to B multiplied by 0.12 divided by 0.12. Okay, so the value of B is what we get when we divide, that's when we divide 7.7 by 10 to the what? 10 to the power of negative 2. All right, so in this case, this is going to be 7.7 multiplied by 10 to the negative 2. Okay, now we can write this as 1.2 times 10 raised to the negative 1. Okay, so the value of B is 7.7 divided by 1.2 times 10 to the, so when we bring this negative 1 up, it will be negative 2 plus 1. That will be negative 2 plus 1. So we are going to have B to be equals to, so this is going to be 77 divided by 12 multiplied by 10 to the negative 1. So how many 12 can we get in what's it called, 77? So we have B to be equals to, that will be 5. Okay, we have a remainder of 17. Okay, that will be 66. Okay, then we have a remainder of, we have a remainder of this 77. So we have a remainder of 11. Then in 100 and what's it called, 110. So this will be 6 points. So what we have here, we're going to have 7 divided by 12. Okay, multiplied by 10 to the negative 1. So 7, we have 77 divided by 12. That will be 6.42 times 10 raised to the power of negative 1. So the magnetic flux density will be 0.64 Tesla. 0.64 Tesla. So the value of B, is 0.64 Tesla. Remember, the unit of B is what? Tesla. And I said 1 Weber per square meter equals to 1 Tesla. So 1 Tesla. So now let's check. Now this is B, the unit is Tesla, but the value for B in this case is 0.37. So this is wrong. Now for option B, we have B, the unit of B is in Tesla, and we got 0.64 as a value of B, and we know that the unit of B is Tesla, so this is correct. Now this is wrong because the unit of magnetic flux is Weber, not for magnetic flux density. So this is wrong, okay? Is also wrong, and this is the answer. So the answer to the question is 0.64 Tesla. Thank you. Hello, welcome. Yeah, we have a question on electromagnetism. An electron moves in a circle of radius 2.0 centimeters in a uniform magnetic field of flux density 170 millitesla. So what is the momentum of this electron? All right, so now this is a question under what we call forces in magnetic field. So it means that to be able to find the momentum, that is to calculate the momentum of the electron, so we need to what? We need to, I mean, it means that we have to employ the use of forces in, under the concept of electromagnetic induction or electromagnetism. All right, let's get into the video. So we have now, the first thing is to identify the parameters. Let's identify the parameters before we now set up the the equation of the different forces. All right, so now we have an electron moving in a circle of radius 2.0 centimeters. So that means that now we have a circle, and this circle is being described by an electronic charge. Okay, the circle is being described by an electronic charge along a path. So that means that now it is moving in a circle along a path, and the radius of the electron, okay, as it moves is given to be 2.0 centimeters. That's 2.0 centimeters. So the radius, okay, the radius is 2.0. Now we have the radius to be 2.0, and we're also giving the magnitude of the what? We are giving what we call the magnetic flux density. So the magnetic flux density is 170 millitesla, and we know flux density is 1 Tesla equals to 1 Weber per square meter, because flux density is the ratio of magnetic flux to cross-sectional area. So in this case, we have our B to be 170 multiplied by 10 to the negative 3 Tesla. So that is the magnetic flux density. Now, the radius, we are given the radius. The radius is 2.0 centimeters, and that will be 0.02 meters when we convert from centimeter into what? Meters. So that will be 0.02 meters. Then also, now that's all that we are given. All right. Now there are other things to also, there are other parameters, okay, apart from these two that we have in the question. Now, the electronic charge, negative charge, you understand? Now, that is electronic charge, that is the electron, because electron is a negatively charged particle, and it is a component particle of what we call cathode rays, okay? So now, so it means that electronic charge, that's E will be equals to 1.6 times 602 multiplied by 10 to the negative 19 coulomb. That is the magnitude of electronic charge. Sometimes we can use 1.6. All right, we use 1.6, or we can also use this. All right, so it's still the same thing. All right, so we have the magnitude of electronic charge to be 1.602 multiplied by 10 to the negative 19 coulombs. Remember, the unit of electric charge is what? The coulombs. All right, so now we have all of this. Now, another thing we need to understand is, now when we say an electron is moving radially, it is moving, in a circle along a path. Now, that tells us that now for the electron to be moving along a path, there will be a force that will keep the electron moving along a path. And we know the path described by the electron is circle. So that means that as the electron is moving in a circle, it means that there will be a radial force, more like a circular force. And this circular force is what we call centripetal force. So we have our centripetal force, okay? Centripetal force. Now, centripetal force. What is centripetal force? Centripetal force is that inward force that will always keep an object or a body moving in a reference circle. So we have centripetal force to be mv squared over what? R. Then also, because the electron is moving, is in motion, so the force that keeps the electron moving in motion, that keeps the electron in motion is what we call the magnetic force. So we have the magnetic force. Let's say the magnetic force is designated as Fm. So we have the magnetic force. So magnetic force, okay, is now, since it is force on an electric charge moving, that means there will be, that's a velocity. So we have EVB. So we are going to set these two force equal. We're going to set this equals to this. So we're going to have our centripetal force equals to magnetic force. And what is centripetal force? We have mv squared over r equals to magnetic force which is EVB. Now when we divide this equation, by v, dividing this equation by v, we're going to have mv over r, okay, equals to EB. That is, the equation will reduce to mv over r equals to EB. Now, then we can write mv to be equals to ERB. mv equals to ERB. Now, what is mv? mv is our momentum. Now, we know that momentum is defined as the product of a body's mass and its velocity. So, and we can designate momentum with this letter. Okay, so I can represent this as, this is the momentum. We have the electronic charge, then we have the radius multiplied by B. All right, so now we have these three, and let's check. Now, this is what we have E, which is 1.602 multiplied by 10 to the negative 19. Okay, multiplied by the radius. The radius is, that will be 2 multiplied by 10 to the negative 2. Okay, multiply by, then we have the magnetic flux density, which is 170 multiplied by 10 to the negative 3. Okay, so now let's get what is, when we multiply 1.602 by 2, then multiply by 170, that would be 544.68. That will be 544.68 multiplied by 10 to the negative 19 minus 2, then minus 3, like that. Okay, we combine the powers of 10. Okay, so 10 to the negative 19 multiplied by 10 to the negative 2, then multiply by 10 to the negative 3. So in this case, this will be 544.68 multiplied by, now we have 10 to the negative 19 minus 2, that will be negative 21. And 10 to the negative 21 minus 3, that will be 10 to the negative 24. So this will be 10 to the negative 24. All right. So now when we write this in, what we call standard scientific notation, so that will be 5.4468 times 10 to the power of 2 multiplied by 10 to the negative 24. And this is going to be 5.4468 multiply by, so that will be 2 negative 24, okay, and that will be 5.4468 multiplied by 10 to the negative 22, and the unit of momentum is the kilogram meters per second, and this is the momentum of the electron. Thank you. Hello, welcome. Yeah, we have a question on electromagnetism. That's Faraday's law of electromagnetic induction. Yeah, the question we have is, well, a coil with 500 turns is placed in a uniform magnetic field. A uniform magnetic field. The average cross-sectional area of the coil is 3.0 multiplied by 10 to the negative 4 square meters. All right, so the magnetic flux through the plane of the coil is reduced from 1.8 multiplied by 10 to the negative 4 Weber to 0 in a time t. All right, so the average electromotive force, that's the EMF, induced across the ends of the coil is 0.75 volts. What is the value of T? Now, first of all, what is Faraday's law? Faraday's law of electromagnetic induction states that the magnitude of the induced electromotive force in a coil is equal to the negative of the time rate of change of magnetic flux linking the coil. So we're going to express that mathematically, using a formula. So now, like I said, according to Faraday's law, which states the induced EMF in a coil is proportional, is proportional to the magnetic flux, the rate of change of magnetic flux, linking the coil. All right, so we have E, induced electromotive force. Then we're also having change in magnetic flux with respect to time. Now, when it is flux linkage, so it will now be multiplied by N. So when we say flux linkage is number of turns or number of loops, multiplied by magnetic flux, change in magnetic flux. All right, then, so what we are giving is, we're giving number of turns. Which is 500, okay? Now, we're also giving the average cross-sectional area. So the average cross-sectional area, is 3.0 multiplied by 10 to the negative 4 square meters. Then also, we're giving the magnetic flux through the plane of the coil is reduced. So which means that the initial magnetic flux will be 1.8 multiplied by 10 to the negative 4 Weber. Okay. Now, the final magnetic flux will be 0. It reduces from, when it reduces from the final magnetic flux to this. So it means that there's a final value. So it now reduces, so that reduction. So we're going to have our the final magnetic flux to be 0 Weber. So that'll be 0. All right. So now the average electromotive force induced across the ends of the coil. So we're giving the EMF, the induced EMF in the coil. So the induced EMF in the coil is given to be 0.75 volts. Now, what is the value of time t? Now, we have the mathematical relationship. This is the mathematical relationship. All right, remember, now this is negative. So, and remember that when we replace the proportionality sign, with equality sign, we're going to have the induced EMF to be equals to negative N change in magnetic flux over what? Over time. So we now plug in the values of the respective values, what we are given. So we have 0.75 as the electromotive force, number of turns, that is 500. Now the change in magnetic flux, that will be 0, negative 1.8 times 10 to the negative 4 Weber. Okay. Now we divide that by, so time, we are looking for time t. So to obtain the value of time t, we know that t will be, so when we switch, so we're going to have t to be equals to negative 500, then negative 1.8 times 10 to the negative 4. So we divide that by 0.75. Now, let's find out what is 500 multiplied by 1.8. That is 900. So then negative times negative, that will be positive. So we have 900 multiplied by 10 to the what? -4 divided by 0.75. Remember, the unit of this is the what? This is the what? Seconds. So 900 divided by 0.75, that would be 1,200. That is 1,200. Then we have our 10 to the -10 multiplied by 10 to the power of what? 10. 10 to the power of -4. So we have t equals to, so when now in this case, multiplying this, we're going to have 0.12 seconds. 0.12 seconds. That will be the answer. 0.12 seconds. So which means the what? Now the time, okay, now we are giving the average electromotive force across the end of the coil. So what is the value of t? The value of time t is 0.12 seconds. Thank you.